true in a particular case. Now, of course, that is not a proof, right? Remember, to prove something, you have to show that it's valid in all cases, right? So, but anyway, it's just to create the plausibility in your mind that that it makes a certain amount of sense. Anyway, here got a cycle, right? And here's the statement that every cycle, here's a general cycle, you can rewrite it as a product of transpositions. These cycles of length 2. So this is in fact a product. Now each of these is a transposition, right? Because it has length 2. There are only 2 terms each time, right? Now, okay. Now it's not. I'm not talking what Barnard's saying in the text. This is now me, right? So I'll try to show you that this is plausible for a fairly simple case, and the cycle now will be of length 3. So I'll just have A1, A2, A3. So like here. Now this is a cycle. So what does it mean? It means that A1 goes to A2, A2 goes to A3, and A3 goes to A1. Right? Cycle of length 3. Okay. Now this is just a list of your objects, right? Remember, the symmetric group just permutes your objects. So here you've got a list. Let's say you put them in a line: object 1, object 2, object 3, object A1 dot 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 dot, object A2 dot 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 dot, object A3 dot dot dot, right? And we're trying to prove that this cycle of 3 elements here, so A1, A2, A3, that will be equal to, have the same effect as these 2 transpositions, where you swap A1 for A2 and then swap A1 for A3. So the net effect of doing that will be the same as doing that. So let me try to show that. Now remember, here's your list, let's say, of your objects in a line. Okay. So I'm going to apply this to this, and A1 will go to A2, so A1 here becomes A2, and then A2 goes to A3, so A2 goes to A3, and A3 goes to A1, so A3 goes to A1. So where you had A1, A2, A3, you've now got A2, A3, A1. Right? A2, A3, A1. Alright, now so that's the left hand side for length 3. Now let's apply these 2. Now remember, the right hand one you do first. Okay? And here's your list again. So this is just the same as here. That's what you start with. It's just your objects that you're permuting. Let's put them in a line, right? So object 1, object 2, dot 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 dot. So so this will be your A1 object. That will be your A2 object, and so on. All right. Now this is a transposition, right? So A1 goes to A2 and A2 goes to A1. So you're just swapping around these 2 effectively. A1 goes to A2 and A2 goes to A1. So that's what you've got here now. See, A1 has become A2 and A2 has become A1. Right? Now apply this one. Now this is your second transposition. It's a cycle, length 2. Right? So transpositions are just swappers. So you're swapping A1 for A3. So this will become A3. There it is. And this one will become A1. There it is. So you end up with A2, A3, A1, which is what you had here. A2, A3, A1. Okay, so it's not a proof, but makes it sound plausible. To make it a proof, you have to use induction, and it gets long and tedious. Right? All right, so we can now make a fairly significant deduction, right? Because what have we done? Now, this part here, we've said that any permutation you can write as a product of disjoint cycles. Like here's a permutation, and these are disjoint cycles, right? So you can take a permutation and break it down, in a sense, into disjoint cycles. Okay, so shelve that at the back of your mind for a moment, because we're going to come back to it. Okay, so you can go from permutation into cycles, product of cycles. And now this part is saying each cycle can be broken down even further into product of transpositions. So broken down into cycles of length 2. Okay. So can you see the logic? If A then B, and if B then C, therefore if A then C, right? That kind of logic. All right. So a permutation goes to cycles, and cycles go to transpositions. Right? So do the logic, and therefore permutations can go to transpositions. Make sense? Right? If A then B, and if B then C, then if A, then C. Okay? All right? Well, here's what I just said is here. So each permutation is a product of disjoint cycles. That's the asterisk. That's this statement here. Okay? But each cycle is a product of transpositions. Therefore, each permutation is a product of transpositions. Let's do an example. Let's say this is a member of what would be S8. Okay? And that's just one permutation of 8 factorial of them. Now, put that into disjoint cycle form. So let's see. Oh, now look, the same, right? So in our product of cycles, there will be no 1 because they're the same. Does that occur again? And the 8 also, right? So 8 maps to 8, the same, and 1. So in our product of cycles, there will be no mention of the 1 or the 8. And that's the case. So we'll only have 6 terms altogether. All right? So 2 goes to 3, 3 goes to 5, 5 goes to 2. So you got a cycle there of 2, 3, 5. There it is. Right? Now on the right hand side, remember the first permutation on the right. And the next one, so 4 to 7, 7 to 6, 6 to 4. So 4, 7, 6, 4, 7, 6. Okay? So there's your product of 2 cycles there. Now, this and this, these are not transpositions because their length is 3. Transposition is a cycle of length 2, remember? Okay, so now using this, or let's the example I did, this is of this form, okay? So this here is just a simple case of this more general one. Okay, so let's forget about this one for the moment. Just use this one because we only got 3 terms, and here we only have 3 terms. So let's use this. Okay. So A1, A2, A3 as a cycle becomes a product of 2 transpositions. Now you do A1, A2 first. Remember the right hand side permutation gets used first. So A1, A2, and then A1, A3. Now in this case, A1, A2, A3, right? So on the right hand side you'll have A1, A2, so it'll be 4, 7. There it is there on the right hand side. And then the one on the left hand side will be A1, A3, A1, A3. So you have 4, 6 on the left hand side. So that cycle becomes a product of 2 transpositions. Transposition, just 2 terms. Okay? So this swaps the 4 for the 7, and this swaps the 4 for the 6. So this applies to the result of the right hand side. Okay, now similar logic, A1, A2, A3. So the right hand side will be A1, A2, so 2, 3, there it is. And then A1, A2, A3. The one on the left hand side will be A1, A3, so 2, 5, 2, 5, there it is. Okay? So this is that, and this is that. So put this here and put that there, and there's your result. So there's your permutation expressed as a product of transpositions, and you can do that for any permutation. You can express any permutation as a product of transpositions, these cycles of length 2. It's quite a powerful result.